Amira Bouguera, so I'm a cryptographer at Consensus. I've been at Consensus for about almost a year right now, and I'm working on privacy-related issues on the blockchain in general, and mostly Ethereum. And today, I'm going to talk about the platform that I'm building, which is called Hellhound, to implement privacy by design tools, which are cryptographic tools for developers to use them. So let me just give you an overview about what I'll be speaking about. So I'll just go an overview about privacy, what is the cryptography role in privacy in general, and what are the cryptographic primitives that are needed to be implemented. Then I'll talk a bit about the state of the ecosystem in general, and some of the weaknesses in the cryptographic softwares, and then some of the famous cryptographic hacks that happened in the past. And then last but not least, I will talk about Hellhound platform and what we offer with our platform, what are the features we offer, and also some of the decentralized cloud computing services that exist already. And also, by the end, I will tell what are the next steps for our project. So let's start. So what is privacy? So many people ask this question, and they also say, we want to implement privacy by design. But do we really know what does it mean, privacy? So privacy, it is a fundamental right that should be given to every single person, to every one of us. And we should be able to control whatever we want to share of information with those who trust, and whatever we want to keep away from those who we don't. And privacy, what does it mean? Privacy means power. And the more we have, the more power we have over our lives. In the last few decades, some of the most powerful institutions and governments have tried to manipulate people and make sure that to use this data against them in some of the social engineering methods in order to extract all sorts of data of people and then use it against them to create an online doppelganger of this person and manipulate it afterwards and make them do whatever they want. And in fact, they managed to do that. And how do they do that? So they collect data over our phones. They collect data from the website, from Facebook, from all from the internet, and they will be using this data against us. So how do we protect ourselves? So what should we do? So privacy program, in fact, is dependent on a security program, because security, we use it in order to be able to encrypt data to make sure that this data will not be shared with anyone. So in fact, also a security program is very dependent on cryptography. So what is the role of cryptography? First thing, cryptography, what does it mean? It means that it's a method to be used to cipher some sort of messages, which means between two people communicating between each other, and they don't want a third party to know what they're saying, so they will add some mathematical functions to this information, and then a third party will not be able to read what's being sent in this information. Now, some of the most famous cryptographic tools and primitives that are being used all over the place, and mostly I'll be speaking of those we are talking all about in the blockchain space. So let me just start by a question. So whoever knows or ever heard about Zk Snark or Zk Snark, or what is the difference between them, could raise their hands. Now, who knows what exactly means and what is the math behind each of these protocols? Could raise their hands. Not that many. So maybe it's not important. Maybe it's not important. Maybe you don't need to know the math behind it. We could just use it. So let me just give you an overview of what is Zk Snark and Zk Snark. So zero-knowledge protocols in general are methods that we use in order to prove to another party in the system that we have some sort of information, for example, and we don't want to share with them this information, but we only send them a proof that we have it. So that is the general idea. So they should be sure that we have information without us having to share this information. So the general idea of the zero-knowledge protocols. What is Zk Snark? So Zk Snark is a protocol that it's used to prove the identity of a person to another person, and then the other person will be 100% sure that is that identity without us having to share any information about the identity. We just share a proof of that. So Zk Snark is something similar. But they are two different protocols. What is the difference? So two of them are non-interactive protocols. What do we mean by that? It means that in order for two parties, approver and verifier, they need to communicate in order to send some sort of challenges to make sure who the person says who he is, then he's correct, and he needs like to prove it. But non-interactive, it means that we don't have to send going and forth messages between these two, prover and verifier. So which is perfect for the blockchain system. So we just publish a proof on the blockchain, and then any verifier at any single point of the time will just come and verify this proof. So both of them non-interactive protocols. Now, Zk Snark, in fact, and one of the biggest problematics in Zk Snark is that it needs a trusted setup. So what is a trusted setup? It means that some of the third parties will work together to create some, to generate some algorithm for proving, some algorithm for verification, and also some secret value. This secret value will be used afterwards to generate this proof. Now, why it's problematic? It's because in Zk Snark, and especially for Zcash protocol, if you may have heard of it, that they use Zk Snark, is that they say that we suppose that this trusted setup phase is secure, which means if it's not secure, then the whole protocol is gone, and we could generate fake proofs. So if we say that these third parties who collude together to generate some value, maybe could collude, maybe like the government could control them, and then we could have fake proofs, for example, for a voting system or something. And also, something not good about trusted setup, that it takes so much time in computation, which means big complexity. Now, Zk Snark doesn't need such a setup phase. Also, quantum safe. What do we mean by quantum safe? We mean that we have some sort of quantum computers that will be able to break some of the cryptographic algorithms, break the security that's behind them. Zk Snark, in fact, they're not quantum safe, which means these quantum computers can break them and we could recover the secret value. So why they're not quantum secure? Because they're based on cryptographic algorithms. They're called pairings. So pairings, in fact, the security assumption behind pairings is the computational Diffie-Hellman, which means, let's say I have a point on an elliptic curve, for example, p, and then I compute this value p with some random value alpha, and I also compute p with some random value beta. The computation Diffie-Hellman problem, it means that it's hard to compute alpha multiplied by beta multiplied by this value p, which doesn't seem like very hard, but in fact it is. So this is the security that's behind pairings. And also it means that also it depends on discrete logarithm algorithm, discrete logarithm problem, which is breakable by quantum computers. We'll be able to break the discrete logarithm, which means in the future these could be breakable. Now, Zk Snarks are not breakable because they only use hash functions, and they are quantum safe. So this is just an example. Now, moving to the next primitives. Who here knows what is homomorphic encryption or multi-party computation? Not that much. Now, who knows what one of them means? Or what are the use cases? OK. I'll give you some introduction about it. So what is homomorphic encryption, in fact? It's an encryption method that allows us to apply some sort of functions over encrypted data. So the encrypted data, in fact, will be random, and in fact you cannot really apply just a function on some random values that you cannot even read. But homomorphic encryption allows you to do that. So meaning have some ciphertext 1 ciphertext 2 computed with the same encryption algorithm, that you will be able to apply some sort of function f, maybe like multiplication, addition, or any sort of operation. And then the value that you will get at the end by applying this function over an encrypted data, if you decrypt it, in fact, it has the same value as if you applied the function over the data in plain text. So why it's important? Now, just to give you the RSA example. RSA is an encryption protocol. So RSA, in fact, the encryption method is we have a message M, and then we do M power some exponentiation E, which is a public value. And then we do this, and that's the encryption of M. So if we do encryption of M1, encryption of M2, if we multiply the first encryption with the second encryption, in fact, the value that we have, it's M1 multiplied by M2, two of them power E, which means as if we applied the multiplication over the plain text, in fact. So this is the multiplication property that some protocols has, and other protocols have addition property that you could have, like addition on ciphertext. So why it's used? Let's say, for example, you'll be able at some point to send an encrypted data to Google. Say, I want to search something, but I don't want Google to know what I'm searching for. And Google can send me back the results and give me what I searched for without them knowing what is the thing that I was searching for. It's perfect, right? Not really. Well, it's still in research phase, these sorts of protocols. But, so anyway, so I was just giving you some sort of example. Now, how to use these protocols? How are we able to use them, in fact, if we don't understand the math? Now, as I said before, maybe it's not important. Maybe that we don't need to understand what's behind it. Now I'll give you some examples of why we need to understand this math, or we need some people to understand it. I'll give you some example about the weaknesses in cryptographic software that have been caused because of this ignorance. The first, some mistakes that in the implementation of cryptographic protocols caused by developers who don't understand what exactly the protocol means. And then I'll give you an example about flaws in protocol layers, such as TCP, TLS, and then side channel vulnerabilities that are on hardware. Let's start with the first one, some math. Okay, let's start with the first attack, in fact, that happened in the PlayStation 3. So what happened in PlayStation 3, that some attacker was able to have root access and was able to recover the private key of the signature and to have root access on the PlayStation 3. So what happened, in fact? Before, let me just give you an overview about the ECDSA algorithm that was used for generating these signatures. So we choose a random value k for each signature that we going to do, for each new signature. And then we compute some R, value R, which is k multiplied by g. G is a public value in the group that we choose to use. And then we compute some R, which is the point of R, modular some Q. And then we compute the signature, which is the inverse of this random value multiplied by the hash of the message. The hash of the message is public value because the message is public, and then the hash we can compute it ourselves. Plus R, which also was generated from the big R, multiplied by X, which is the secret key in our algorithm. And then we output the signature. Now, the vulnerability was that Sony was using, in fact, the same random value K, and they were not generating a new value K each time they were computing a signature. So they were using the same K. So what happened because of that? So if we take a first signature, S1, so it's K minus 1 multiplied by the hash of the first message plus Rx. The second signature is also K minus 1 just because we use the same random value, multiplied by the hash of M2 plus Rx. Why it's the same R? Just because we use the same K. And then it generated the same big R. Now, if we do S1 my S2, we recover K minus 1 multiplied by the hash of M1 minus the hash of M2. S1 minus S2 is a public value. It's the signature. The hash of the first message, the hash of the second message also is a public value. So which means we could recover the inverse of this K, which means we could recover the K. And while we recover the K, we just apply it to this algorithm, and then we could recover the secret value X, and then we could recover the private key. So that was an implementation bug that happened because developers just didn't understand that they needed to generate a new value each time. Now let me give you a second example about one of the most famous attacks that happened on the TLS transport layer, which called the Heartbleed. So what is the Heartbleed attack? In fact, it was applied on the Heartbeat extension on the OpenSSL library in TLS. So the Heartbeat is a way of keeping communication alive between a server and a client. So what the client sends, he sends some sort of message, let's say OK, and OK has 2 bytes. And then the server will just reply with the same message plus the same size. Now, in fact, the attack, is that the attacker sent a message OK, but the size, he sent a different size. This big size, and which is not the size of OK, of course. So if he sends that to the server, the bug, what it caused that the server would reply with OK, and then replied with values from the memory of the server of all the messages, unencrypted messages that were stored, just to send the correct value, the correct size of what the client asked for. What are these unencrypted messages? There could be passwords, they could be private keys, all sorts of unencrypted data. So that was a certain bug that was on OpenSSL cryptographic libraries, also because of implementation problems. A third example was side channel attacks that happen for hardware, let's say smart cards, some computing hardware solutions. So what happens, I'll give you just an example of these sort of attacks. For example, like power consumptions, and this is a sort of attack that could be applied. So you just like calculate the power, the consumption, for example, a timing of consumption of the functions that we calculate, let's say multiplication, squaring, that the hardware will execute to compute the private key. So in fact, in the RSA protocol, in order to compute the private key, we just take the encrypted messages that I showed you before, which is M multiplied by E, and then we just, explanation E, and then we just do a second explanation with D, which is the private key. So in order to compute this private key D, so what we do in RSA, we use 5 squaring and 1 multiplication. So when we measure, in fact, because squaring and multiplication have different measures, so we will be able to find the multiplications that were done. And since the multipliers that have been used are only 30, we have 32 possibilities of multipliers, then we will be able, in fact, to recompute the private key from such a flow. Now, I gave some examples. Now I'll let you know what we propose in our project in Hellhound. So now, how developers, can do, for example, like on Morphic encryption, zero-knowledge protocols, apply these secure multi-party computation, which I haven't talked about, but maybe in the next time. In the easiest, how can they use them in the easiest, most secure and efficient way, according to the current state of the art of these protocols, and without them having to have all the knowledge of the math behind it? Because I just give you some really simple examples of the mathematics behind these protocols. And it's more complicated than just these. So how can we do that? Well, Hellhound is your solution. You just use Hellhound. Now, what we offer a recommendation engine for cryptographic libraries. What do we mean by that is that, for example, a developer would say, I want to do blind computation. I want to do computation. I don't want to publish my data unencrypted, and I also want to verify this computation. And it's okay. I don't care about complexity. I care more about privacy. Depends on what you care about more and more. So then there is an algorithm that will be running and will be choosing from a certain database what sort of libraries that will be better used for what you need. And then it will give you back a result. It will not send you back the result. It will just tell you, OK, we found a perfect solution. Do you want to use it? And then after that, we have a network that will do blind computation using Morphic and multi-party computation protocols, and then verify these computation. And also, we have verified crypto libraries. So what do we mean is that all the cryptographic libraries that exist so far, especially for these new protocols, are not verified, which means they could still have some of the security bugs that people have just didn't find them. And we propose to do verification for these libraries in order to mitigate against some of the side channel attacks, some of the cryptography implementation of cryptographic protocols. And this is just an idea about the architecture we want to create. So the client would communicate, and then there was the recommendation engine, and it check with the state of the art, and then we could do computation with multiple nodes, with multiple hellhound nodes, and depending on their reputation, it's all depending on a consensus protocol behind these nodes, how do they compute, and also a staking system in order to make sure that these nodes are honest in doing the computation. And then we publish verification afterwards to the blockchain. And then we get results and then verify it. So that's just an overview of what we propose. Now, some of the ideas of all the already existing platform that do these type of computation, such as Golem, who we're presenting, I guess, in this conference, Is Zk, Enigma. Enigma, in fact, they were doing also off-chain computing, but they're using hardware solutions. We propose something different. We propose multi-party computation to include different nodes to be able to do this computation. Enigma will be mostly focusing on their private smart contract platform. Also, Is Zk, which is a distributed platform for doing computation. So these all are different projects. They propose different solutions for these similar problematics that we find right now in the blockchain, that we have privacy issues and also scalability issues. We try to solve all these problems, and some of these projects propose solutions, and we are one of these projects. So what are the next steps for our project? So we will be launching our version 1 of the crypto map of what we will be using as primitives, cryptographic primitives. We'll be launching it in GitHub by September. And then we'll be releasing our white paper by the end of the year. And then this is just the beginning, and just stay tuned. And this is the team. So we are just 2 people. So we are 2 people, a cryptographer and blockchain architect, and we are based in Paris. But we are part of a bigger team called It Compute, which is at Consensus, and we work on distributed computation, off-chain computing solutions on the blockchain, also privacy-related issues. So join us, and let's build privacy by design. Now, we are currently recruiting. Please check our offer, and please, if you're a full-stack developer, please check our offer and join us to work together. Thank you, everyone.